already made the.
Okay, perfect. Then I will be sharing my screen. And okay, so can you see my screen?
Yes.
Yes.
Yes, I can see.
Riza, if you could also start recording.
Yeah, it's already started.
Oh, it's already done. Perfect. All right then. Weijie, can I start?
Oh yeah, sure. Please
Okay.
go ahead. Thank you.
Perfect, thank you. Then I would like to open this second week of our seminar series, which is entitled OTFS-enabled satellite communications. Our seminar series is co-hosted by Orthogonal Time Frequency Space Special Interest Group in Satellite and Space Communication Technical Group of IEEE. And also Satellite Mega-Constellations Special Interest Group of SSC, and also Space Air Ground Integrated Communication SIC. So first, I would like to introduce myself. My name is Karabulut. I'm a professor in the Department of Electrical Engineering of Polytechnique Montréal, and I am the secretary of the IEEE technical group on satellite and space communications, and I am also the chair of the Satellite Mega-Constellations Special Interest Group. And before giving the opening remarks, I would like to thank Professor Weijie Yuan for all his work and efforts in organizing this. I would like to explain why we believe OTFS-enabled satellite communications is rather important. Now, there is a justification for this two-week seminar. I think you are all perhaps in the domain and you are very familiar, but I would like to just remind everybody about what is going on in terms of the evolution of communication technologies. When we are looking at the sixth generation networks, most of the underlying components and the changes are well matured in terms of the discussions. We have a good understanding of the new components that will be addressing these sixth generation networks. And one of these changes in this vision would include the new networking element. So that would include the non-terrestrial networks, and there will be a extensive cooperation between terrestrial networks and non-terrestrial networks. And when we look at the non-terrestrial networks, mega-constellations, and they are also possibly supported by additional components, such as high-altitude platform stations and UAV-mounted drone swarms, would be of key interest. When we are talking about 6G, of course, it may look a bit distant, but when we look at the changes in the 3GPP domain, looking at the evolution of fifth generation networks with release 16, we already see these components with the particular properties. So the non-terrestrial networking elements are here to stay, and they will be evolving to satellite networks, and satellite networks currently composed of a bit hundreds and perhaps thousands of satellites. But in the near future, it's forecasted that there will be dense satellite networks based on the FTC filings. We can see on the order of 40,000 LEO satellites. So when we look at these networks, it is important to design communication systems that accommodate the evolving characteristics of these networks, and they mainly change on the channel and the networking aspects. Now, when we look at the OTFS waveform, based on its flexibility and its customizable form, we believe it's an excellent fit for these satellite networks, hence the motivation for our seminar series. And so it gives me great pleasure to welcome everybody with these two interesting talks by Professor Yi Hong and Professor Weijie. And with that, I would like to thank you for your attention. And if you have further comments or questions, please do not hesitate to email me at güneşkurt@polymtl.ca. So thank you, and I'll pass the floor to Weijie.
Okay, yeah. So allow me to have a brief introduction of Professor Hong. So I think if you have done researches on OTFS, you must have known very well about Professor Hong. So Professor Hong is currently an associate professor in the Monash University. So she served as a member of the Australian Research Council College of Experts. And also she is a senior member of IEEE and the IET Fellow. So Professor Hong has served as the tutorial chair, the TPC chair, the general co-chair, and the publicity chair for several conferences, especially on information theory. So Professor Hong is also the associated editor for some IEEE journals. So today, Professor Hong will introduce the OTFS and the delay-Doppler communications. So especially the applications to the LEO satellite communications. So I think, Professor Hong, can you share your screen?
Sorry. So thanks very much. Thanks, Weijie and Professor Güneş for the nice introduction. And also, thanks for the invitation. I'm delighted to deliver this invited seminar. So today, I will talk about my recent research on OTFS and delay-Doppler communications. So the plan of my talk is to first introduce the fundamentals of OTFS to enable the beginners to have a simple understanding of this technique. And then at the end, I will discuss the potential applications of OTFS in LEO Satcom. So here is the outline of my talk. So after introduction, I will present the wireless channel representation, and then I will discuss the OTFS modulation and channel estimation. So finally, I will discuss the potential application of OTFS to LEO Satcom. So here, I also provide you the links to download the sampled OTFS MATLAB code. So since 2017, so our team has been working on this topic, and we have generated some interesting results. So all these results were summarized in this recently published book entitled Delay-Doppler Communications, Principles and Applications by Academic Press. So in this book, we have introduced some fundamentals such as the OTFS input-output relations and ZAC transform for OTFS, the OTFS transceiver structures. And also we introduced some advanced topics such as OTFS channel estimation and detections. And also we introduced the applications to Mimo and multi-user cases. So also we have included a complete set of OTFS MATLAB codes for simulation purpose in this book. So if you're interested, you are welcome to read our book. So let's get started. So my research focuses on the design of modulation technique for high mobility wireless communications for 5G and beyond. So now let's start with an example. So where I consider a future high mobility communication scenario as shown in this picture. So you can think of it as an emerging mass transportation system, which consists of a large number of moving objects, such as flying drones, high-speed trains, and self-driving cars. So in this scenario, there is a base station which is transmitting signals to this white vehicle via a standard wireless multipath channel. And due to the large number of high-speed moving objects acting as scatterers, so they introduce to the channel severe Doppler effects. So as a consequence, the performance is significantly degraded. So to support a highly reliable communication and to combat severe Doppler effect, I consider the design of modulation technique as a solution. So motivated by this, before I introducing OTFS, so I first recall two basic concepts for wireless channels. The first one is the delay spread, as shown in this example. So in the base station, okay, there's a base station which is transmitting signals to the mobile via a multipath channel of two paths. And the receiver received superpositioned signals over these two paths. And one is from the line of sight path, the other is the reflected path. So due to different path lengths, so the arrival time of the signals will have slightly different delay. So the delay of line of sight path is given by tau1, which is the line of sight path length divided by the speed of light. And so similarly, you can write down the delay of the reflected path tau2. So the delay spread is given by the gap between the last versus first arrival. And then the received signal as shown here. So it's the superpositioned signals from these two paths. And each path, you can observe the received signal the signal as experienced path delay and scaled by the path gain. So next, I will introduce the mobility to this scene. So I replace the static mobile by this moving vehicle, which is moving at velocity v towards the base station direction along line of sight path. So due to relative motion between the transmitter and receiver, it introduces to these two paths different Doppler frequencies. So the Doppler frequencies of the line of sight path is given by V1 Hertz, which is the carrier frequency Fc times the velocity of the vehicle divided by the speed of the light. And similarly, we can write down the Doppler frequency of the reflected path, which is V2 Hertz, which is carrier frequency Fc times the velocity times cosine theta divided by the speed of the light, C. So the V cosine theta, you can think is the velocity along the reflected path, where the theta is the angle between the reflected path and the moving direction of this vehicle. So the well-known Doppler spread is given by the maximum versus minimum Doppler shifts. So then the received signal is also, as mentioned, the superposition of signals from these two different paths. So in each path, the signal S experienced the delay, path delay, and also scaled by the path gain, like the previous case. But different from previous case, it also experienced the time-varying Doppler shift incurred, time-varying phase shift incurred by the Doppler shift. So this forms a time-varying channel of two paths. So now we can extend to the arbitrary p paths, and we can write down the received signal, which is a superposition signal of these p paths. And in each path, the signal S experienced path delay tau I and scaled by the path gain, and also experience a time-varying phase shift incurred by Doppler shift. So then we can group these first two terms, which gives you the time-variant impulse response for that path. And then we can also write received signal in terms of convolution. So at the second equation. So in general, the RT, the received signal, is a convolution between the time-variant channel impulse response and the transmit signal ST. And in particular, the time-variant impulse response is given by the summation over p paths, and in each path, you can tell you have the path delay tau I and Doppler shift Vi and path gain Hi. So next, we want to make a plot of this time-variant channel impulse response. So in fact, this we obtained from this book chapter. So we observe that the time-variant channel response rapidly change along time axis. So for such a time-varying channel, next we want to know how the current modulation technique, Ofdm, behaves. Okay, so I assume that you all familiar with Ofdm. So I will provide a quick overview on Ofdm. So Ofdm is a modulation technique that divides a frequency band into multiple orthogonal subbands. And in each subband, place subcarrier spectra to carry information symbols. Or in other words, Ofdm is a multi-carrier modulation technique that adopts multiple orthogonal subcarrier spectra to carry information symbol, as shown here in frequency domain. So you observe in this plot, there's multiple orthogonal sync pulses representing multiple orthogonal subcarrier spectra to carry information symbols. Okay, so prior to transmission, typically you can add the guard intervals of sufficient length to combat multipath delay. So Ofdm is known to combat multipath delay. And one of the key points of Ofdm is try to keep multiple subcarrier spectra as orthogonal as possible so that it can simplify receiver detection. For example, you can use the one-tap equalizer. So this is Ofdm. So now we want to know, and the time-varying channel with severe Doppler effect, how Ofdm behaves. So this is shown in this figure in frequency domain. So we observe that these multiple subcarrier spectra lose orthogonality. So for instance, if you want to get sampling of this peak value of the sync pulse, you also have the interferences from neighbor subcarriers. So this interference is called the intercarrier interference, ICIs. So this is the well-known interference. And of course, Ofdm has schemes to combat or mitigate the ICI effect. For instance, in 5G, the one trivial solution is to increase subcarrier spacing to accommodate this ICI effect. But it works for well for low Doppler effect. But here we consider is a severe Doppler effect, as mentioned in the first example. A large number of high-speed moving scatterers introduced to the multipath channel, each path multiple high Doppler shifts. So if you keep increasing subcarrier spacing, you lose a lot spectral efficiency. On the other hand, if you don't mitigate or completely remove ICIs, so you lose significantly the performance. So motivated by this, so we are looking for modulation technique that can combat severe Doppler effect. So in 2017, Hadani et al. From Cohere Technology proposed this orthogonal time frequency space modulation called OTFS, which has demonstrated outperformance over Ofdm in high mobility scenarios and can combat well the severe Doppler effect. So the key idea of OTFS is to work in the delay-Doppler domain rather than the time frequency domain that is associated with Ofdm. So the reason is that the wireless time varying channel, and if you plot the channel response in time frequency domain, you can observe that the channel response is quite dense and it rapidly changes along time axis and frequency axis. But if you convert to delay Doppler domain, the channel becomes sparse and it's much easier to handle. So that motivates us to work in the delay Doppler domain. So since it's related to wireless channel, so next I will talk about wireless channel and explain why the delay Doppler domain is preferable. So for wireless channel, let's first look at the different representations of linear time variant wireless channel. So we can start with the time variant channel response, GT-TOR. So based on Fourier-based transformations, we can convert it from time domain to time frequency domain to obtain the time frequency channel response that is associated with Ofdm technique. Or you can also convert it to delay Doppler domain to obtain delay Doppler channel response that is associated with OTFS technique. So now we want to see the relations between delay Doppler and time frequency channel responses. So the reason we want to see the relations between them is because one is associated with OTFS and the other is associated with Ofdm. So their relation is explained in these two equations. So basically it tells you if you have the time frequency channel response, so you can take a two-dimensional Fourier-based transformation and which involves two terms Vt and Ftop. And there's a minus sign in between. So this forms the 2D symplectic Fourier transform. And based on this transform, we can convert the time frequency channel response to the delay Doppler one and vice versa. So this is their relation. So next, I will narrow down to talk about the delay Doppler channel response for a specific channel. For example, a multipath channel of P paths with each path have gain Hi and delay tau I, Doppler shift Bi. So then we can write down accordingly the delay Doppler channel response, which is summation over P path. Each path you have equivalent path gain Hi prime, delay tau I, and Doppler shift Bi. So then based on this multipath channel P paths, and then we can plot this delay Doppler channel response. And we also plot this channel response in time frequency domain and make a comparison. So in figure A, it showed the delay Doppler channel response. Figure B showed time frequency channel response. So in figure B, we observe the channel response rapidly change along time axis and along Doppler axis. But surprisingly, if you observe from delay-Doppler domain, the channel response becomes sparse and also become time independent. Once you fix delay, you basically can capture the corresponding Doppler shifts. So this motivates us to work in the delay-Doppler domain. And up to now, I'm talking about the continuous time channel response. So next, I will continue to talk about discrete time channel response. But to save time, I skip all the sampling details and parameters. I will just talk about how we use time, frequency, and the delay Doppler grids to represent discrete time channel response. So the grid in blue is the time frequency grid, which has n equally spaced time slot, each occupy capital T second. And the frequency axis have m equally spaced subbands, each has delta f hertz. And delta f is just 1 over capital T. And then once you do a conversion to convert it to delay Doppler domain, so the delay Doppler grids has n equally spaced Doppler gap, and each has 1 over nt hertz. This is a Doppler resolution. So in delay axis, we have m equally spaced intervals, each occupy 1 over m delta f second. This is a delay resolution. Okay, so then based on this delay Doppler grids, we want to represent a multipath channel p path with the following delay Doppler channel response, which is a summation over p path. Each path have a gain hi prime and have delay ti and tau I and the Doppler shift vi. So to represent this channel, first we assume that both Doppler and delay resolutions are sufficiently high. And then these p paths can be represented by this p distinct grid points. And if you can think third dimension, there will be this p grid point will have impulses representing the corresponding path gains. Okay, so for instance, if this point represents the ith path, you can go horizontally, find the corresponding delay index, multiply with the delay resolution. This gives you the path delay. And you can also go down to hit the Doppler axis, find the Doppler indices, and multiply this Doppler resolution. That will give you that path Doppler shift. So in this way, you can represent the discrete time channel response. So this is up to now is all about the channel. So now we are ready, we move on to talk about OTFS modulation. So, so I will start with the OTFS modulation and the demodulation structure proposed by Hadani et al. In 2017 WCNC. Because after that, we also identified that this can be simplified to be a simplified version. So I will talk about that in a minute. So in this figure, it shows the OTFS modulation demodulation diagram. So in this diagram, it basically tells us that you place information symbols in the delay Doppler grids of size Mn, and then followed by the inverse symplectic finite Fourier transform that converts information symbols from delay Doppler domain to time frequency one, and followed by the Heisenberg transform, which is equivalent to an pulse shaping and Ofdm modulator that converts time frequency samples to the time domain signal and transmit. So then once you received at the receiver time domain signals, then you process it with the Wigner transform, which has opposite function to Heisenberg. So basically it is equivalent to a pulse shaping and Ofdm demodulator that convert time domain signal to time frequency domain samples, and followed by symplectic finite Fourier transform converted to delay Doppler domain, and you can add detection, etc. So based on this diagram, the red box showed you the delay Doppler domain operations. thanks to ISFFT and SFFT. And the blue grid showed you the time frequency domain operations. So how do we understand OTFS? There are many different understandings about OTFS. So here I find for people who is familiar with Ofdm, the following is an easy understanding to start with. So it said that the OTFS is equivalent to Ofdm with 2D unitary precoding, okay, in the time frequency domain, which spread each information symbol equally in M subcarrier and N time slots. So then based on this diagram, we can further write down the delay-Doppler domain input-output relation. So to write down this relation, we first assume, for instance, a noiseless case, and also make ideal pulse assumption. So the ideal pulse assumption means that both transmit and receiver uses ideal pulse shaping waveforms that is satisfied by orthogonal condition. So it implies the signal pulse is perfectly localized in time and frequency and will not cause any leakage from one symbol to the next or one subcarrier to the next. So under this assumption, we can write down the received signal in delay-Doppler domain, which is nothing but 2D circular convolution between the information symbol and the channel. Okay, so how do we understand that? We can understand by using this figure. So in figure A, for instance, we place the information symbols equally spaced in delay-Doppler domain, and we transmit them over the delay-Doppler channel with the channel response in B. And in C is the received signal, which is a collection of spreaded information symbols. So that is the symbol, information symbol got spreaded by the channel, and the spreading pattern is exactly based on the delay-Doppler channel response. So this applies to all these information symbols. So you have a collection of the spreaded information symbol at the receiver. So then you can do a detection to recover them. So of course, this is just an intuitive example. So in reality, you can also place them next to each other in figure A. So then at figure C, you get the received, which is a collection of spreaded information symbols with certain overlapping, but you can design properly the detection to recover them. So this is a high level understanding of the delay-Doppler domain input-output relation. So then you can continue, you can write down the time frequency input-output relation with these ideal pulses. So basically it's a simple multiplication between the time frequency samples with the time frequency channel response samples. So of course the ideal pulses are not realizable. So in practice, you can use practical pulses, for example, rectangular pulses. Then you can write down the time frequency domain input-output relation as follows. So we know that they do have both ICI and I size. But the good thing about OTFS, so as showed in this published paper in 2018, so the good thing about OTFS is you can convert them in delay-Doppler domain. And surprisingly, in this paper, we find that both ICI and ISI becomes very simple phase shifts that associate with the channel delay and the Doppler types in the delay-Doppler, delay-Doppler indices in the delay-Doppler grids. So then you can easily correct them at the receiver side. So this is basically the idea based on this 2017 modulation demodulation structure. So next, I will talk about OTFS input-output relation in matrix form. So here, I first want to talk about this modulation, demodulation architecture can be reduced to simplified forms. So let's first talk about this, and we recall the diagram I just introduced before. And this is a modulation diagram. OTFS modulation diagram. And here, different from before, I just put more details in each block. So first, look at we can place information symbols in these delay Doppler grids at size Mn to form information symbol matrix X. Then followed by the 2D ISFFT operation, which can be split into two operations. The first operation is we have the row-wise, along Doppler axis, we have a row-wise endpoint IFFT followed by the column-wise endpoint FFTs. So these two forms the 2D ISFFT operation that converts information symbols from delay Doppler domain to time frequency domain. And then followed by the Heisenberg transform, okay, which is power shaping, and the column endpoint IFFTs that convert samples from time frequency to the delay Doppler domain, and then do a parallel to serial conversion, adding CP, and you forms a time domain OTFS signal that contains n blocks, and in each block m samples. So here we easily observe that these endpoint FFTs, okay, followed immediately by endpoint IFFTs. So these two operations can be canceled out. So the whole thing has reduced to a simplified form, which is the information symbol matrix in delay Doppler domain, followed by the row-wise endpoint IFFTs, and then followed by the column vectorization. You take each column and pack them to a longer sequence and adding CP and full transmission. So this reduced structure is nothing but the well-known inverse Zag transform. So actually it tells you the transmitter is doing the inverse Zag transform. So also we can write down the math representation. For example, the information symbol X in delay Doppler domain, and followed by the row-wise endpoint IFFTs represented by Fn dagger. And then you do a column vectorization. So this forms a time domain transmitted signal vector. So also it is worth to mention here is that this simplified transmit structure is also equivalent to the known vector Ofdm or AOFDM that used to propose the full static multipath channel in these first two papers. So, and also the connection to OTFS is discussed in the last paper. So these two schemes were only proposed for static multipath channel and was never investigated for high mobility channels, because for high mobility channels, the input-output relation would be different, and also the receiver detection and channel estimation would be different. So this is a transmitter part. Now we move on to receiver part. Based on the simplified structure, we can also have the receiver side. The receiver side, once we receive the time domain signal, okay? So after removing CP and do a serial to parallel conversion, you can form the received signal matrix, and then followed by the row-wise endpoint FFTs and converted to the delay Doppler domain. Okay, so, and this structure is nothing but the Zag transform. So we can write down the math representation. Once you have the received time domain signal vector R, you can do a devectorization. That means you form a matrix, let's show as showed in this gray box. And then you followed by the row-wise, the endpoint FFTs. So this is nothing but a discrete Zag transform. So this basically, for Zag transform, you can find in this first paper, the details about the properties, and also it's summarized in the book. And basically from these two slides, it tells us another perspective of understanding OTFS is transmitter and the receiver are in fact are doing inverse Zag and Zag transformations respectively. So then based on this input-output relation, next we also want to know the OTFS channel matrix representation. So then we studied the channel matrix representation in both time domain and the delay-Doppler domains. So in time domain, the channel matrix basically is a square matrix of represented by G here of size Mn. And it has a following representation. So it's a summation over p pass. Each pass you have gain hi prime and followed by the delay matrix and followed by the Doppler matrix, delta Ki. So this delay matrix is the permutation matrix to the power of Li. Li is the delay type. So this matrix to the power of Li represents, you will have Li times forward cyclic shift of this permutation matrix. And the delta Ki is the Doppler matrix, is a diagonal matrix. So each element, diagonal element, is associated with the Doppler shift Ki. So basically, if you use this channel matrix G, multiply the transmitted signal vector S, what does that mean? It means that each pass introduces Li forward times cyclic shift of the transmitted signal vector S, and then modulated with the carrier at frequency Ki, which is associated with the Doppler shifts. So this is a time domain channel matrix. So then we move on, we can convert it to delay-Doppler domain. This is the delay-Doppler channel matrix. I skip all the details and let's just talk about the last expression. So it's a summation over p path. In each path, you have effective channel path gain hi prime and times the matrix Ti. How do you understand this matrix? This is like the ith path, the effective matrix for the ith path. And also in this paper, we have studied this matrix Ti. We find there's only one non-zero element in each row, and the position of the value of this non-zero element depends on the delay-Doppler values. So since due to this unique location of this non-zero element in each row, okay, so then we can make a summation over p paths over all this Ti matrix. So then we obtain the final channel matrix, which we prove have only p non-zero entries in each row and column. And it also tells you this channel matrix is a sparse, has a sparse, simple sparse structure. So then the channel is sparse. And based on this channel sparsity, we can design properly detection channel estimation. So based on that, I will skip the OTFS detection. I will directly talk about OTFS channel estimation. So for OTFS, channel estimation is very interesting. So the channel estimation can be done in quite different approaches. So for example, in the literature, there's a delay-Doppler channel estimation, delay time channel estimation, time frequency channel estimation, etc. So here I will briefly introduce the idea from our published paper, which is the pilot-aided channel estimation in delay-Doppler domain. So to introduce this idea, first I consider a 2x1 Mimo Otfs example, as shown in this picture. And here I also consider the pilot-aided channel estimation in delay-Doppler domain. So left-hand side is the transmitter side, right-hand side is the receiver side. In the middle, there are two different delay-Doppler channel responses. So at the transmitter side, we place one pilot for each antenna in the delay-Doppler domain and make sure there is a sufficient spacing in between to avoid interference at the receiver side. So then we transmit them over their distinct delay-Doppler channels. And then at the receiver, this is what we got. So first we observe both pilot and the receiver got spreaded. And the spreading pattern is according to their corresponding delay-Doppler channel response. And then based on this, we consider the threshold-based channel estimation. That is, you set a threshold and you compare with the spreaded pilot impulses. So if you set a threshold, for instance, compare with impulse, and you compare the magnitude with the threshold, if it's greater than the threshold, then this path is considered. And also this path coefficient can be computed. Otherwise, you ignore this path. So in this way, we do the channel estimation. So this is a sketch of the idea of pilot-aided channel estimation in delay-Doppler domain. And also, apart from pilot, we also care about the data symbols. So that's why in our paper, we proposed the transmit symbol arrangement for CISO OTFS, as shown in figure A in delay-Doppler domain. So in horizontal axis is the delay axis, vertical is the Doppler axis. Okay, so then, for instance, you can place the pilot symbols in this blue grid, and outside is the red grids. We place zero guard symbols, and outside the black grids, we place data symbols. So the key idea here is that when we place zero guard symbols, we must look after, place zero guard symbols along sufficient areas along the delay axis and also along the Doppler axis to avoid the interferences between the pilot and the receiver, and the data symbols at the receiver side. For instance, if you place pilot along delay axis in LP, this location, okay, so then you should place zero guard symbols at this LP plus minus L tau. L tau is the delay tab associated corresponding to the maximum delay. And similarly, when the location of pilot is KP in Doppler direction, then you place zero guard symbols at least to look after KP minus or plus to KV. KV is the Doppler tab associated with the maximum Doppler shift. So in this way, we can go to figure B, which showed the receiver symbol pattern. So we can see at the receiver, inside the blue grid are the spreaded pilots and outside the datas. So we observe there's no interference between the spread pilot and data symbols. And then based on these spreaded grids, pilots, okay, we can do a channel estimation, and based on estimated CSIs, we can use the remaining data to do data detection. So in this way, we can do channel estimation data detection in one OTFS frame. So this is a CISO case. So next, we can also extend to Mimo OTFS. So Mimo OTFS, first we consider an example, for example, 3 times 1 Mimo. And the top 3 transmit symbol pattern for each antenna, transmit antenna. And the bottom is for receive antenna, the receive symbol pattern. So the transmit symbol pattern, in each transmit antenna, the symbol pattern is exactly like a CISO case. The only thing worth mentioning is when you place pilot for adjacent antennas, you must guarantee sufficient spacing in between, which is beyond L tau, which is corresponding to the maximum delay. And in this way, you can avoid the interferences between spreaded pilot at the receiver side. So at the receiver side, you can see the blue grid contains a spreaded pilot, for instance, from antenna 1. The purple grid is for a spreaded pilot antenna 2, and the green grid is spreaded pilot from antenna 3. So then you can do an individual channel state CSI estimation. And based on estimated CSIs, you use the remaining data to do the data detection. So this is a Mimo case. And in our paper, we also studied the multi-user uplink downlink pilot symbol and pilot symbol arrangement. So that is the delay Doppler channel estimation. So in the recent 1 year, we also developed a delay time channel estimation. So if you're interested, you're welcome to read our paper in TWC and WCL, and also summarized in our book. So at the end, let me see time. So at the end, I will talk about OTFS application to LEO Satcom. So I think LEO Satcom naturally fits in the high mobility communication scenarios as I introduced at the beginning of the talk. So for example, we can assume that the LEO satellite is transmitting signals to ground users, and both of them are in motion. And also the ground user is surrounded by a large number of high mobility moving scatterers that introduce to the multipath channel, the severe Doppler effects. So this motivates us to study the potential applications of OTFS to LEO Satcom. And also here in these slides, I list a few publications. Of course, I believe that nowadays you have much more papers in this topic. So to save time, I will only talk about my recently published paper in ICC workshop. So to talk about this, I will quickly briefing you the LEO satellite background. So the LEO satellite circled the Earth at an altitude of 500 to 2,000 kilometers and orbit the Earth at the speed of 7 to 8 kilometers per second. And for example, a LEO satellite velocity at 1,500 kilometers altitude is 7.1172 kilometers per second. So when the carrier frequency, for instance, is 20 gigahertz K-band, so then the maximum Doppler shift can be up to 400 kilohertz. So then motivated by this, we considered in this paper, the LEO satellite is communicating with ground user where they both are in motion. So first we want to study the performance of CISO OTFS or Mimo Otfs in LEO Satcom. So first we need to establish the channel. So here, to get an easy start, we consider the very simple channel model as shown here, which is a multipath channel of p-paths with the delay-Doppler channel response given here. And for this multipath channel model, we adopted the NTN, the TDL channel model in 3GPP. So basically, for each path, the delay types is given here is TI norm times DS desire. So TI norm is for the ith path, the additional delay over the first arrival delay. And DS desire is just a scaling parameter that makes the delay spread values spans to the range in channel measurement corresponding some typical 5G evaluation scenarios. So it's a list of numbers. It depends on the evaluation scenarios. You can choose the one fits in your setting. So this is the delay types. And for Doppler shifts, basically, we also consider the very fundamental ones as shown in the standard. So first we look at frequencies. So FC plus FZ, FC is the carrier frequency and the FZ is extra frequency shift introduced by satellite. So basically this FZ is defined by velocity of a satellite divided by speed of light times the carrier frequency times cosine theta. So cosine theta is the satellite moving direction with respect to the propagation line from satellite to the ground user. And then this frequency after we can compute, and then you can compute the V cosine alpha cosine phi divided by speed of the light, C. So let's first look at this V is the ground user speed. And phi is the angle between the moving direction of user with respect to the projected plane from the satellite, this phi. And alpha is the elevation angle. So V cosine alpha cosine phi is basically the speed along the propagation line from satellite to ground user. So then this is the basic Doppler shift that we applied to each Doppler type. So then after following this channel model, we studied the CISO and Mimo OTFS. So basically for CISO OTFS, the input output relation is straightforward, is like before, is the channel matrix G and multiply the transmitted signal vector S. And then the G is the matrix I just introduced. The channel matrix is square matrix of size Mn. It contains each path the path gain HI prime, followed by the delay matrix, and followed by the Doppler shift matrix. Okay, so, and then we can extend to the Mimo case. So the Mimo case is also straightforward. So where the channel matrix G Mimo, so it depends on the transmit receiver antenna numbers. For instance, you make arbitrary NT transmit and NR receive antennas. So you will form NT-NR links, and each link will share this matrix G. Okay, this G is given here, like CISO case. So this forms this G Mimo matrix. So for instance, this sub matrix G, the size is Mn. So you have NR of G. So and then column you have NT of that G. So the size will be NRMN times NTMN. So further, we also make simplification. We assume that each Mimo link and share the same number of multi-paths and with the same delay and Dopplers. So then you can write down a simplified version of channel model, which is a summation of the P path, and then followed by a collection. For the ith path, you have a collection of Mimo path gains, and then chronica with delay matrix and Doppler matrix. So then based on this, we also studied the antenna correlation impact on this Mimo OTFS system. So for this antenna correlation, I will skip the detailed derivations, but instead I will just intuitively talk about this. So the antenna, basically antenna correlation will impact this path gain matrix, this Mimo path gain matrix. We'll introduce some extra correlations on the HI. But then we adopted in the paper, we adopted standard whitening transformation to remove this spatial correlation on the channel. So based on that, we conduct in figure A. So we're using massive passing detection. So then we can see that the pink plots represent the Ofdm performance. The blue plots represent the OTFS performance. And the dashed line represents the CISO case, the solid line represents the Mimo case. So overall, OTFS outperform the Ofdm in this setting. So then we converted to the Mimo OTFS 2x2 Mimo. Then we studied the antenna correlations impact on the performance. So basically to compare, we also plot a benchmark that without any correlation. So as in the solid black line. And we also plotted the Mimo case with antenna correlation in the dashed line without doing any decorrelation help. So the red one is with the high correlation with the parameter vector 0.8, and the blue one has the low correlation 0.2. And then we apply the whitening transformation to remove the spatial correlation on the channel. Basically, for the low correlation, we can get very close to the performance of no correlation. So overall, that in conclusion, I think considering the potential applications of OTFS to LEO Satcom, there are many other practical challenges, such as the channels involving time frequency Doppler, time varying Doppler shifts, and latency issues, and Doppler estimations for different use cases in different geographical locations. So all these require future careful studies. So at the end of my talk, I also want to give my special thanks to my colleagues, Professor Emmanuel Viterbo, Karaj Taj, Amit Bora, Kwa Fan, and Raviteja Pachava So they had fruitful discussions with me from time to time and also assisted with the slide. So thank you very much. I hope
thank you, Professor Huang.
Yeah.
This is Zhiqiang, and I will chair the question and answer part. And thanks, Professor Huang, for her very comprehensive talk, and with both breadth and depth of the fundamental knowledge of OTFS modulation, and also the application of OTFS in LEO satellite. So let's see the questions. First, Vignesh asked the questions. So every channel path has an equivalent Doppler spread instead of a Doppler shift, as my understanding. Will it be discernible or resolvable from the delay-Doppler channel response?
So every channel path has equivalent Doppler spread with.
I think she or he is asking, yeah, if the Doppler
same,
spread
you mean,
of a path can be resolvable.
So it's, I think it's also depends on the multipath and the delays, right? If you have a different multipath with different delays, and you have a similar Doppler tab, it still belongs to different path, I think. Did I answer the question?
I'm not sure what exactly Vignesh means, but my understanding is he or she may be asking for each path, it may has more than one Doppler shift, but in delayed Doppler domain, we just model one Doppler shift for one path. Is this but actually?
So you mean maybe the Doppler resolution is not sufficiently high that a few Doppler can be quantized in the same Doppler bin. So
yes,
you can really cannot distinguish them. Yeah, that is the burning problem, I think. So you will sacrifice certain performance, but compare with Ofdm, I think you still have the gain, because nevertheless. So even in static multipath channel is equivalent like a layered Ofdm, which is still outperform the standard Ofdm.
Yes, I agree. Second question from Yaru Shan, and she's asking what if happened if the maximum Doppler shift is larger than the subcarrier spacing? And under these conditions, can OTFS still overcome the Doppler effect?
So typically this can be tuned, right? If you know the maximum Doppler shift, you will set probably M and N and subcarrier spacing and the duration T. But if in practical scenarios, if you really have the hardware constraint or some latency constraint or other constraint, that this is happened, I think it's still like the previous case, the answer. So it still is better than the standard Ofdm because in the, if this thing does not really overcome things, it still have like layered Ofdm structure. So you can basically gain over standard Ofdm because you get more channel diversity from the delay side in that case.
Yes, yes, and I also agree. And the third question is from Yan Shisun, and he's asking, how does OTFS performs on the static channels, and can OTFS outperform Ofdm on the static channels?
You mean the static multipath channels? So if for static multipath channels, we have published a paper that showed OTFS is equivalent to the vector Ofdm, or so-called later called the asymmetric OFDM, AOFDM. So basically, they are layered OFDM structures. So it does outperform the traditional OFDM over the static multipath channels. And the reason is still you get more channel diversity from the delay perspective over the traditional OFDM.
And there's another question also from Yaru Shan is for the embedded pilot channel estimation schemes you presented under fractional delay and fractional Doppler. Shall we set the whole frame as one pilot and the other position as only one pilot and the other positions as guide? Since like the whole delay-Doppler domain grids will be influenced due to the fractional delay and Doppler.
Okay. Okay, that's a very good question. So in fact, with the fractional Doppler, you can use zero guard symbols along the entire Doppler axis, the entire endpoint. We call it the full guard scheme. So where the pilot is placed. So then, but you can still use the remaining grid towards in delay direction. So that is my opinion. So of course, if you use the entire everything to do the channel estimation, you can do a better one, right?
Yeah.
The entire frame. But in my opinion, if you have a fractional Doppler, you can just use the you can place the pilot and then use the entire guard along Doppler axis to look after that. And you can still use the remaining grid point in the delay directions.
Yeah, but the point of Yaru may be in the case of both fractional delay and fractional Doppler.
So in the fractional delay, so yeah, I agree. You can do the entire frame. But if you do an entire frame to contain one pilot to do the channel estimation, then you will take a risk because next frame can have a slightly channel varying. So you maybe your channel estimation is not you know, from one frame to next. This frame you estimate the channel, maybe next frame will change. The channel will have slightly changed. So yeah, you can do that, but it could also have some consequences.
Yes. And another question is from Neil Baker, and he said a larger gain is shown for OTFS over OFDM for LEO case. But if the common large Doppler shift is pre-corrected, would OTFS still show a large advantage over OFDM?
This, I think, is the same as a static multipath channel case. So if you remove the severe Doppler effect and purely compare OTFS versus traditional OFDM, OTFS should gain because it is a layered OFDM structure. And if you consider time domain, according to channel diversity, you gain more channel diversity from delay aspect if completely remove the Doppler impact. So this is my my answer. Yes, that answer is yes.
Okay. And there's another question. Is there a way to see OFDM as a special case of OTFS, and is possible to share some of the operations to build up the two modulations? I think is yes.
That's a very good question. I think definitely. I think when OTFS, we can think is n block. Each block you contain m samples. But if you reduce n to be 1, it is OFDM, right? So is it possible to share some operation to build up the two modulations? to build up to modulation. Is that means relation? So I think I've talked about this is OTFS. You can think is if you think about from the AOFDM perspective. So basically, you can think is each row can be a OFDM symbols, and then you can do a parallel endpoint IFTs on each these symbols, but then followed by the column, row column interleaving. You take each column and pack them in the time domain. So I would say it's yeah, it's a pre-coded OFDM on the high level interpretation of OFDM versus OTFS. Yeah.
Okay, so I will choose last questions because it's almost midnight in Australia. So the last questions is, could you briefly explain the pilot requirement? Could you also briefly comment on the pilot requirement, especially for high mobility channels? What does it mean?
Pilot requirement. Yeah, that's a good question. I think pilot requirement, you mean pilot SNR. So and also surrounded zero guard symbols for channel estimation. Basically, it depends on the channel. If it's very how to say severe Doppler effect, okay, and to estimate the channel, and you need to have a large zero guard symbols, and then you can also set the pilot SNRs. So if you increase pilot SNR, so relatively you can kind of increase the performance. But if you can reduce pilot SNR, okay, so you kind of have reduced performance. So there is a trade-off between the pilot SNRs and the zero guard symbols, that coverage, okay, and then the channel estimation outcome. I think it's always a trade-off, and also, of course, spectral efficiency and overheads.
So I could not ask all the questions listed here due to the time limitations. And thanks, Professor Hong, for your excellent talk and for your answers and discussions on the questions of the audience.
Thank you very much. Thank you, Zhiqiang. And thanks, Professor Gunes and Weijie for the nice invitation. Thank you very much. So I will stop sharing, yeah?
Oh, yeah, please. So let's go to the next talk. Next talk is from Professor Jia Xu, and the talk is on. Sorry. The talk is on OTFS-enabled reliable LEO satellite communications, a killer for severe Doppler effect. Dr. Jia Xu received both his master and PhD degrees from the University of Southampton, UK in 2010 and 2015. He was a research associate with Lancaster University during 2015 to 2017. Then he became a research fellow with the 5GIC University of Surrey, UK from 2017 to 2018. Since 2018, he joined Xidian University, China, and now is an associate professor with ISN. His current research interests include resource location in wireless communication, wireless systems, reliable LEO satellite communications, convert communications, physical layer security, millimeter wave satellite communications. He is now serving as an associate editor for electronic letters and an editor for International Journal of Communications Systems, and is serving as a guest editor for China Communications. So, Professor Josh, yeah, I will stop my sharing and you can begin your talk.
Thanks for Professor Wei, and thanks for your invitation. Let me share my screen. Sorry, can you see my screen?
Not yet, John. Not yet.
Oh, sorry. It's not okay. Okay, can you see?
Yes, we can see now.
Okay, shall I start?
Sure, sure. Go ahead. Yeah.
Yeah. Today's talk is about OTFS-enabled reliable LEO communications, and it was supposed to be me and my colleague Professor Zhan Li, because she's on her way trip back to Xi'an, so unfortunately she can't make it. So that will be me to give this talk. Professor Zhan Li and I are from Hadani University, and this is an outline of my talk today, and there will be 6 parts. And the first part is about an overview about the LEO satellite communication systems, and the second one is about OTFS modulation and how to apply it in LEO satellite communication systems, and which is followed by 3 case studies. And finally, I will give some interesting future directions and challenges. So why is satellite? In current 5G system or 5G networks, we all know that 20% of populated area on Earth is already covered by wireless services. However, the rest of 70% of ground lands or depopulated areas are still no data services, like oceans, like some rural or remote areas. So we need satellite communications to give a wide and seamless coverage in future. So as we know, we have in past years, we have GEO, MEO satellite systems. Why LEO satellite is talking by a lot of people, especially from academia and the industrial world, because it has shorter latency, lower path loss, smaller size, and cheaper cost for implementation, and also the higher throughput. Let's see 3 typical LEO satellite communication systems. The first one is OneWeb system, which is launched by UK, and there are 720 satellites in total, and there are 18 orbital planes, and the orbital height is about 1,200 kilometers. And so far as we know, there are almost 420 satellites running, and the rest of them, the latest news for OneWeb is announced by they have an agreement with New Space India Limited. And the other one is the most famous one, Starlink. And we have, as we know, the Starlink has different orbit planes, and range from 1,000 to up to 1,300 kilometers heights. And in total, there will be 46,000 satellites. So far, already have, I think we already have 2,000 satellites running. The last one is Telesat from Canada, and this is a system having the number of satellites over 117 satellites running. However, due to the price issues, this system is pushing out its completion to 2026. All the typical satellite systems are featured by, so far as we know, all featured by single carrier transmission schemes. Let's do a brief summarize for the typical LEO satellite communication systems. In future, we think the quantity of LEO satellite will be 100 orders of magnitude, a hybrid networking of multiple orbital planes, and the latency will be reduced by an order of magnitude, and also the data rate will be increased to gigabytes levels. However, as we may be aware that if we using the satellite communication, we probably have this kind of equation for Doppler frequency shift. As we can see, we have the subcarrier carrier frequency and the orbit height and the elevation angle. If we increase as we can see from this table here, if we increase either carrier frequency or the height of the elevation angle, the Doppler shift will be increased as well. So that's why if we have a severe Doppler shift, the link reliability will be a very an important issue to need to be discussed. In future, people are talking about LEO satellite communication systems are going to use higher and higher spectrum. As we can see, Starlink is planning to use V-band or E-band in the near future, and more users are allowed to be accessed. So that's so the academic work are talking about if we can use the multi-carrier system transmission schemes, and especially the Ofdm scheme, because in current system like IP star satellite system, this is a geo satellite communication system. It already used it has already used the Ofdm scheme and proved the advantage or the performance of Ofdm scheme. So, however, if we using the higher, if we're using the higher frequency bands, the Doppler frequency will be, Doppler effect will be a problem to be dealt with. So how to mitigate the Doppler effect in LEO side communications scenario? We summarize 3 main techniques for mitigate the Doppler effect. The first one is we can have a proper setting of subcarrier spacing. To be honest, we need to increase the subcarrier spacing according to the 5G standards. The carrier, if we need to combat the Doppler frequency shift, we need to have 10 times of maximum Doppler frequency shift. However, according to the current 5G standards, the maximum carrier spacing is about 240 kilohertz. And in LEO side communication systems, even if we use the EHF bands, the subcarrier's frequency should be much larger than 600 kilohertz, which certainly apparently cannot be met. The second technique for mitigating Doppler effect is to use the frequency locked loop or phase locked loop scheme. The phase locked loop is the frequency locked loop is used to tracking the residue frequency shift with a large band. And followed by this, we can use the phase locked loop to accurate tracking the phase of the signal. However, these 2 techniques are used for a single carrier scenario. If we use the multi-carrier system or multi-carrier scheme, we need to apply them to a single carrier by single carrier. This will definitely increase complexity by a very large scale. So the complexity of using PLL or FFL is a big issue. The last one, the last technique for mitigating Doppler effect is to use the palette-based Doppler shift estimation scheme to estimate the frequency shift. Then we do the compensation at the receiver side. However, as the Doppler shift become very severe, we need to increase inserting many palettes in the transmit frame or transmit signal. So this will largely reduce the overall spectrum efficiency. And at the same time, estimation accuracy is a problem due to the high varying rate of Doppler frequency shift. Last, this one is also cause a very high implementation complexity. So let's move to the second part. This part is about the OTFS, the basic concept of OTFS modulation, and how OTFS has advantages over Ofdm systems. I will skip this part because Professor Hong has already given a very detailed introduction about the modulation and demodulation process. This just an overlap. So this is some basic idea of how to modulate and demodulate. That's what you can see. So just skip to the advantages of using OTFS over Ofdm. The first one is apparently OTFS is non-sensitive to Doppler frequency shift. This is a simulation result we've done for comparison, and we have the 4-quam modulation symbols, and we have the 30 gigahertz carrier frequency. The velocity is about 500 kilometers per hour. And as we can see, OTFS has a significant performance gain over the Ofdm one, and also which proves the reliability advantage of using OTFS. The second advantage is about reducing channel estimation overhead. Currently, we have different velocities, we have different Doppler frequency shifts, and we need to estimate the channel. In high mobility scenario, we need to either add pellets in front or insert pellets in the signal. Currently, we have the OTFS tested. It's around even for 500 kilometers per hour, we have around 4% of overhead for OTFS. However, from the current standard, either to 820.11g or 11n, we have these figures for Ofdm is around 8.3%. This is not for the high mobility scenario. If we considering the same scenario as this part, this figure will go up to 20%, almost 20%. So the number of pellets under Ofdm is much lower than Ofdm. And at the same time, we need CP we also need the CP for OTFS, but differently. For OTFS scheme, we can realize the CP in a blockwise instead of doing the carrier by carrier in Ofdm scheme. The third advantage is the low PPR characteristics. As we can see, we do some simulations and we found that the OTFS PPR is always lower than the Ofdm. It is simply because by using the ISFFT and because the OTFS has a longer frequency, which allow to average out the energy per bit. So that's the advantage coming from. And also the lower PPR feature will help the practical implementation, especially for cheaper or low requirement for amplifier, which is good for the uplink. So let's move to my third part. So I will do a performance analysis for OTFS-based LEO satellite system. The motivation of this work is about to see how OTFS outperform Ofdm in combating severe Doppler effect. And we also want to prove to see how the cooperation transmission used in the LEO satellite communication system, because we know the transmission link is quite quite big. So we need to see if we need the cooperation from UAV or how the cooperation performs. And we consider the long downlink case, and we have three nodes. We have the source nodes and destination, and we have a cooperation from UAV. And the channel are modeled by the shadowing rise feeding, and the channel from UAV to destination is modeled by the Garmin M distribution. Apparently, there are two phases. One is a direct link and a direct phase, and the other is cooperation phase. This is the equation one, which is for the transmission in TF domain, and this is basically the OTFS modulation. And I will skip this part. And let's see this one, equation 4. This is for the received signal either by the destination node or in the first phase by the UV. And we can express it in a matrix form, and in equation 5. And apparently, this capital H is a block circulant matrix. In order to remove the intersymbol interference, we need to apply an equalizer at the receiver side, and we just apply the simplest one, the FD LE scheme. And after the equalizer, the linear equalizer, we have this equation 6. As we can see, this part is a surprise noise term, and either for at the UAV side or the destination node. And after that, we apply the direct phase, and we apply the MRC maximum ratio combining scheme to get the final signal at the destination node. We have the mutual information obtained by destination node, giving this equation 7. We need for equation 7, we want to see how the reliability of OTFS performs. So we define the outage probability by equation 8, where the RB is the required data rate. As we can see, this small gamma is the lower implement gamma function. And the parameters in 8, alpha and beta, are related to the parameters of SR channel, Garmin M channel, and path loss, frame size or modulation size, the transmission power as well. In order to analyze this equation, we need to find the PDF of a SR variables, which is this part. And however, it is impossible to derive the closed form for this PDF. So we use a moment matching approach to approximate the PDF as a gamma function. Based on that, we can derive 2 lemmas. One is for UAV cooperation. This is a condition for using UAV cooperation. If we have this condition, we can have a positive gain from using UAV cooperation. And this mu, this parameter mu, actually reflects the channel quality of relay transmission, which is a inverse of channel quality. And the second lemma is to compare with the Oftm scheme. The outage of Oftm is can be achieved by the, or can be analyzed by the similar approach as the OTFS, and then we do some simple computation. We have this number 11 equation for the condition of achieving performance gain by using OTFS. Here are some simulation results. As we can see, we have the height of satellites to be 800 kilometers, and we have the height of UV to be 20 kilometers, and carrier frequency 15 gigahertz, and modulation for QAM. And from this figure, we can see the outage probability will always get better as long as we invest in more and more power, transmission power for the direct link. And we also note that there is a small intersection between these two curves, and this is actually for the cooperation and the non-cooperation. It actually reflects that at this area, the condition for lemma 1 cannot be met, or we can see the cooperation link is quite poor. Here is another simulation result for comparing OTFS with Ofdm. And interestingly, we see this part, the Ofdm is actually has a better performance than OTFS, and we can see this part actually is from the outage probability higher than 0.5. Which is, however, this is not practical. As we can see, if we have a outage probability higher than 0.5, the communication currently cannot be used. So apart from this, the OTFS has significantly performance gain than the Ofdm. And we also note that if we use larger modulation size, the performance gain will be enhanced as well. So let's move to the second case study of our work, which is optimal power allocation for LEO Satcom communications system based on OTFS scheme. As Professor Hong introduced, the modulation of the signals in DD domain and the OTFS scheme almost experience the same, exactly the same channel gain. So that's so in that case, there's no point to do the power allocation in DD domain. So, however, after ISFT, the signal is modulated to the traditional TF domain. So, however, in TF domain, the channel, the different signals also experience different channel gains. So that's why we are thinking about how the power allocation in TF domain to impact the performance of OTFS. So in this case, we consider the downlink of a LEO Satcom communication system, and we have the simplest scenario. The transmission and the receiving nodes both of them will have the number of antennas for 1. And we have the Nagami distribution feeding. And here are some other assumptions for the system. And after we do the power allocation at the receiver side, we would like to use 2 different equalizers. One is ZF, the other one is MMC. There are 2, I think the most 2 famous linear equalizer for OTFS. So let's see the result. After some calculation, we have the SNR for ZF and the SSINR for the MMC case. And we, in order to find the optimal power allocation, we would like to optimize or maximize, to maximize the equation 1 and equation 2. And we see the optimization results, which is given by equation 5 and equation 8. We can formulate this optimization problem, and it's a very simple one. We can solve it by using the Lagrangian method, and we formulate the Lagrangian cost function, and we can directly solve it by some simple mathematical works. And we can see this is the results for optimal power allocation. We compare them with the Ofdm case, and surprisingly, we found that actually, in order to achieve a good reliability performance, we need to invest more power to the poor subchannels in depth domain. It is exactly contrary to the water filling method in Ofdm. So this is an interesting finding from our result. And also we compare our optimal power allocation method with the water filling and equal power allocation method, and so it is. So we have proved that our optimal power allocation scheme, how this is a theoretical the best one, and apart from that, we also found the ZF equalizer is actually more sensitive to the power allocation in TF domain by comparing these 2 curves, the triangle one and the square one. And the last case study is about the OMP-based signal detector. Why we study this detector from the previous case study, we can see we use traditional linear detector for the receiving OTFS receiving signals. However, in LEO Satcom communication systems, especially for the uplink, there are many random interference in the complex space environment. Some of them are dynamic and random. So we need to deal with this complex interference scenario. So we need, so in that case, the linear carrier, the linear equalizer cannot be used. So must go to nonlinear one. However, as we know, the nonlinear, like traditional MP detector, it has a very high complexity and cannot be directly used in many scenarios, especially for LEO side communication scenarios. So as we can see, the equation 1 is for a receiving signal at the LEO side communication system is for the uplink. This part is for the random interference part. So we need to, in order to deal with this problem, we need to mitigate the intersymbol interference and the second random interference term. And for this sake, we developed the OMP scheme. This scheme is designed in the DD domain instead of TF domain in other traditional Ofdm schemes. So when in the OMP scheme, actually there are two parts. One is a linear equalizer, and one is a linear estimation. The other one is a nonlinear estimation. The linear estimation is for mitigation or for mitigating all two elements, the effect of multipath interference or the intersymbol interference. And the nonlinear part aims to reduce the Gaussian noise and to improve the quality of that estimated signal. By iteratively running the two parts, we can have a good result thanks to the sparsity of DD channel domain. We can run few iterations to get a very converged result. So by applying the OMP in DD domain, we can have a low complexity to apply the nonlinear detector, and the complexity is around mn to this level. And also the OMP-based scheme has less restrictions on channel matrix than MP or AMP. And the OMP-based scheme is potentially applicable to a wider range of linear equalizer than AMP, which is good for deep learning. Let's see some performance results. We do some BR performance to see how it performs. As we can see, if we increase transmit SNR, all the channel quality is becoming better. The BR performance of OMP, either OMP or MP or other cross-domain detection. This is actually cross-domain detector developed by Weijie, and we can see if when we use the OMP scheme, the iteration goes up to 5, and the performance of our OMP can outperform the cross-domain scheme and become very close to the theoretical the best MP scenario. And this is another simulation result for considering the channel estimation errors. If we have different channel estimation errors, we have the multipath, the 4 multipaths, and we have different variants of channel estimation errors. You can see the OMP scheme is quite robust, especially when the channel condition, when the transmit SNR is low. Finally, I will finalize my talk today by giving some future research directions on OTFS-based LEO side communications and give some challenges. The first one is I think we still need to do a lot of work for designing low complexity detectors, especially for nonlinear detectors. Some people are starting to apply machine learning methods to nonlinear detector process, and however, they haven't considered the computation or energy consumption limitations. So this is an interesting research direction. The second one is to design the cost accuracy trade-off for channel estimation. As we can see, Professor Hong also gave some channel estimation method, but so far as we know, if the Doppler frequency shift become, especially the maximum Doppler frequency shift becomes very large, we need to increase the guard band or the guard area to do the pallet to protect the pallets. So do we have a better solution for this for this problem? Probably we have a cost and accuracy trade-off to find the answer. The third one is delay constraint multiple access. In future, LEO side communication system will service different kinds of users on ground, and the different of users they have probably they have different mobilities, such as people keep static, or cars or trains or other users. We have different scenarios. We have many scenarios on ground. So how can we design a generalized multiple access scheme for the satellite for the LEO satellite communications based on OTFS scheme? And the fourth one is about energy efficient beamforming design. This beamforming design, I think, is completely different and much difficult than the on-ground transmission. The biggest problem is to do the beam alignment and beam tracking, especially when we have the very frequent orbital displacements. Because people are talking about when we go to higher frequency bands, certainly we need to use directional transmission. And for example, the millimeter wave communications, we need to have definitely need to have the directional transmission. So the beam alignment and tracking, I think, is very challenging in the LEO side communication scenario. The last two are about the coordinated transmission. As my previous slides, we have a very raw study about giving a UAV cooperation. But if we need to cover many ground users in practical system, one UAV cooperation is not enough. So we need a network, a relay or cooperation network to help the LEO side communication system to build up a high reliability network. The last one is about the security. People are talking about LEO side communications probably for a few years, but few study I found that few study are talking about security issues in LEO Sat communication, especially when applying the OTFS scheme. As we know, the OTFS scheme will have longer frame length and have longer, bigger transmission distance, and this means that it has a higher probability to be dispersed in the space. So so how can we build up a new security system or a security network or security basic algorithm from transmission layers to application levels? That's a very important question for future study. I think that's all for my today's slides and presentation. Thanks for your listening. And do you have any questions? Will be.
Thank you, Professor Zhi, for your wonderful talk with a detailed introduction of the satellite communication and the main advantages of OTFS modulation for LEO satellite and some case studies. Very interesting talk. And hi everyone here. Oh yeah, hi everyone here. If you have any questions, please type in the chat, and I can see it, and we can have a little bit discussions. So one question from me, Professor Shi. You mentioned in one slide that in satellite communication systems, even the Doppler has a Doppler variation rate, as you mentioned in one of the slides in the beginning. Does it mean the channel is changing so fast, even the Doppler, does the Doppler shift will change during one OTFS frame?
Yes, I think that's one aspect of the Doppler variation rate. The other is about the different paths, multi-paths. Different paths will have different Doppler frequency shifts. So that will be challenging if the Doppler frequency shift changes during each of the paths. I don't know if I answer your question.
I mean, just for one path, if its Doppler shift will change during one OTFS frame.
I think in that case, we haven't reached to that study, but I think that will be an interesting research topic to deal with, because in that case we don't know the maximum Doppler frequency shift, so we can't. For example, when we're talking about channel estimation, in that case we don't know how to design the guide band for pellets. So that's very challenging, I think.
Yes, I see.
Fortunately, as I know, the Doppler variation rate is not that high in practical system, and probably we give a big range and we can cover that.
Okay. So there are some questions pop up in the chat section. A question from Gunners, Professor Gunners. She's asking, could you please briefly discuss the possible advantages on OTFS in key generation?
Sorry, in key
generation.
Oh, key generation. Oh, okay. Sorry. It's very hard.
Sorry, I wanted to mention about the follow-up on the fourth item of the future directions that you mentioned. That was my question. Thank you.
Okay, the key generation.
Yeah.
Okay. Actually, sorry. To be honest, I'm not a security guy, so I haven't done a lot of research in the security field. So I think the key generation for LEO Satcom communication will probably be different, completely different to the ground case, on ground case, because the synchronization is a big problem. How to do the synchronization to apply the key generation? I think that's the key issue. Because I haven't done some work on key generation, so just an idea to post here. So probably I'm not correct.
Many thanks, Professor Shi. I think it provides that there may be very interesting points there. So well noted. Thank you.
Thank you, Professor.
Thanks.
Yes.
Yeah, and the second question from Emmanuel Viterbo. He is asking, have you considered low complexity detection, such as maximum ratio combining detection with complexity big O proportional to MNL, where L is the number of delay paths, which is independent of the number of Doppler?
No, I haven't considered it. I just considered two basic equalizers. One is DF1, the other is MSE. So I haven't tried that. I would like to see how they perform, probably in future.
Yeah, I think this is the recently published paper by Viterbo's group, and Professor Hong has shown this paper in her slides.
Okay,
Yeah.
I would love, I'm definitely learning. I think it's just the same, similar level of complexity as the other linear equalizer. Am I right? Probably. I see the ZF is about M times N times L, something like this.
Okay, so the third question is from MGH, no name here. Could you please introduce which channel model do you choose in the simulation and the parameters that you have used? Okay,
Because I mainly considered two different channel models. One is the shading rise, which is a typical channel model, I think, for LEO Satcom communication scenarios. The other one is Nagami M feeding channels, because some other people also use Nagami M for LEO Satcom communications. So, and the parameters, I can't remember. Let's back to the first one. I think the first one has some. Yes. Sorry. I think this is the one. This is a published paper. Probably you can find from my TVT paper this year. I think the paper has been given here. This one, can you see it? This one. Now the detailed parameters are here.
Okay, thanks. So if there's no more questions, I think we can finish this talk.
Thanks very much. Thanks very much for your invitation, and good to see you all.
Thank you for giving us this wonderful talk. Professor Grunes, do you want to give some final remarks?
So probably I can stop sharing my screen.
Yeah, please.
And I would like to thank again to Professor Huang and Professor Xi, and also Professor Wei for hosting the Q&As, and also Professor Weijie Yuan for being extremely instrumental in organizing this talk. And I would also like to thank all the participants. Thank you. And once we have the recording available, we will be posting it over LinkedIn, and we'll be distributing. Thank you so much, and have a good rest of the day, or good morning, perhaps it's bye bye now.
Good evening. Good evening from China.
Thank you.
Yeah.
Bye.
Thank
Bye,
you all.
bye.
Thank you for all the participants. Bye bye.
Bye bye.